So first, what do we mean by internal forces? When we talk about internal forces, in general, we have seen together in previous chapter how to calculate reactions. And reaction are external forces on a system, okay? But why internal forces are important? Because, for example, if you are designing a beam in a building, okay? So the beam will support a very high load, and I should take into consideration what is happening inside the material, because if I exceed the capacity of the material, it can lead to rupture. Okay, so internal forces are very important to study in order to make sure that my structure is able to support the loading exerted on it, and we don't have rupture or failure of my structure. Now, what are the types of internal forces? As you can see here, as we said, you have a beam here, okay, and you are applying a certain load on it. You have a fixity at A. So the external load is P1, P2. The external reaction is the reaction at the fixity. And now, what are internal forces? Internal forces and moments can take place anywhere at any section. For example, if I say I am interested in finding what is happening here, I can cut my beam, okay, and when I cut my beam, since my all my system is in equilibrium, so if I cut a part, then also this part is in equilibrium, okay? And when you do a cut, the internal force becomes external, okay? So in this way here, you have, let's say, if you have a x, a y, and there is a bending moment at A, to have equilibrium, you should have a force opposing a y. We call it shear force. Why we call it shear force? Because it is in the plane of the section. You should have a force opposing a x, so it should be directed to the left. This is called the normal reaction. And you have also a moment needed to oppose MA. Okay, so it should be in the clockwise direction. And then you will have equilibrium. Okay, here, when we put MB in this way, it will be negative, because when we do calculation, MB should be in the opposite direction, and the same for M. We will see together that we have a certain convention for shear, normal force, and bending moment. I will introduce them after. So always we put a V in a way to rotate clockwise about the end of the beam. So here, if you look at your figure, okay, if you look at your figure, you have that the shear is downward. Why? Because look, it should rotate. Always the shear force, which is in the plane of the section, should rotate in the clockwise direction about the extremity of the cut. Okay? For example, now, this is why if you do a cut and you take the second part, if you choose to do the analysis of the second part, you will take V upward, because V should rotate in the clockwise direction about the end of the V. And why we do this? We do these conventions because if you take the analysis of this part or this part, you should obtain the same result. Okay, you should obtain same V, N, and N. And you know that by principle of action reaction, if V here is downward on this part, on the other part it will be upward. So to obtain the same value, if I take this section or this one, we follow this convention that the shear should rotate clockwise about the end of the beam. Now, for the normal reaction, what is the convention? For the normal reaction, the convention is that this reaction should cause tension. So if I take this part, okay, N should be directed to the right to cause tension. And if I take this part, N should be directed to the left to cause tension. Okay? And finally, for the bending moment, the condition is the following. The positive direction of the bending moment should be chosen in a way to compress the upper part of the beam. So look here, this is the direction. I am compressing this part of the beam, the upper part. Okay? Now, if I take this part of the beam, then this is the upper part here. My moment should be in the clockwise direction to compress this part. Okay? So always I should follow the convention to know which direction I should put for M. And in calculation, when I do calculation, I can have positive M or negative M. Okay, so let us continue now. You can have internal forces in 2 dimensions or 3 dimensions. Okay, so in 2D, it is just you have a shear force. The force in the section plane is called shear force. The force perpendicular to the section plane is called normal force. And the moment is called bending moment because it will tend to bend your structure. Okay. Now, in 3D, you have several internal forces. First, in the 3 directions x, y, and z, you have a force and a moment. Okay. Now, what is the name of these forces and moment? For the one that is perpendicular to the section, you have this is the normal force. It's called normal force. And the couple that is perpendicular to the section is called torsional moment. Why it's called torsional moment? Because it tends to do torsion to the structure. So as you can see, it will rotate it about, it will do torsion about its axis, its perpendicular axis. Now, forces that are in plane of section are always called shear forces. But here in 3D, you have 2 shear forces, one in Z, one in X. While, for example, in 2D, you have only shear force in the Y direction here. Can you please mute your microphones, guys? Can you please mute your microphones? Okay. So, we have also the moment. Just one second. Okay. So, for the moments, okay, if you have moments vectors along the section plane, then they are called bending moments. So here in 3D, you have 2 bending moment components, one in Z, one in X, which are the axis of the cross section, and you have 2 shear forces V, Z, and Vx. Okay, while in 2D you have only 1 shear force and 1 bending moment. Let us do an example to practice on internal forces. You have, in this problem, determine the normal force, shear force, and bending moment acting at point B of the 2-member frame shown in the figure. So here, if you want this chapter, if you know to deal with previous chapter, this chapter is very simple because it's similar to finding reactions. Okay, so what we want to do here is to determine the internal reactions at point B. Now, in order to do this, always remember that before I do the section, before I do my, to find my internal forces, I should find before the external forces, okay? Because if I do a section and I don't know what is the reaction at A, for example, I cannot solve for my unknowns. Because once you do the section at B, you will have automatically 3 unknowns, which are the normal reaction at B, the shear force at B, and the bending moment at B. So if also you didn't calculate AX, AY, then you will have 5 unknowns and you cannot solve. So always in a problem where you want to find internal forces, the first step is to find your external reaction. Okay? Now here, if you want to find the external reactions, let us look at what we have here. We will take this part. Okay? Why I will take, you can take this part here. What are forces acting on this part? You have a pin at A, so we have AX and AY. Okay? And here, who will tell me CD is what? We call it what from the previous chapter, you remember? It's a 2D force member. Okay, it's a 2-force member. A 2-force member is a member for which we are applying forces only at 2 points, which are here C and D. So we can say now that the force along the force of on C will be along CD, because CD is a two-force member. So I have it. This is the force at C. So now I have three unknowns, which are AX, AY, and the force in C, FC, and FC. Okay, so now since I have three unknowns and I have a 2D problem, equilibrium problem, I can write the three equations of equilibrium for part AC. Okay, now to find the equilibrium relations, first I should reduce my distributed load. Okay, my distributed load is a rectangular distributed load, so I can reduce it into one resultant force, and it is acting at the middle of my distributed load, because my distributed load is a rectangular part and the center is at the middle, so it's acting at a distance of 4 feet from A, and the resultant force magnitude is F resultant, equal to what? The area of the distributed load equals to 8 times 50, 8 times 50, which is equal to 400. Okay, now it is very simple. I want to calculate AX, AY, and FC, knowing that I have a one force of 400 lb acting on my system. So first, the first relation is sum of X equals 0, sum of forces along X equals to 0. What do I have along X here? I have AX and I have the projection of FC. Okay, so if you assume that AX is like this, okay, then you might get a negative result for AX, because FC will be like this. Okay, so AX, you can expect that AX will be negative, because this force FC has a positive X component, and it should be opposed by AX. So if you keep AX like this, you will obtain a negative result. So if I write my equation, I have AX plus FC. Now I should project FC on X-axis. Okay, so if you want, this is a review for the exam. It's true that it's a new chapter, but we are using the concepts of the previous chapter. So here, this is F, my force along CD. As you can see here, they gave me the distances here 4 and 3. Okay, so I can say that, so this is 4 and this is 3. I need now cosine alpha because I'm projecting on X. So it's 4 over 5. Okay, so I should multiply FC by 4 over 5. Okay, and this is equal to 0. This is my first equation. Equation number 2, a sum of forces along y equals to 0. Along y I have AY plus FC times sine alpha, which is 3 over 5, equal minus, for my distributed load, I replace it by one force, and which is 400. So minus 400 equals to 0. Okay. Now, if you want, I can give you a certain hint here. If you want to calculate Fy in Ay in a simple way and Fcy in a simple way, what can you say? Who will tell me? You know, in y direction you have a symmetry for the distributed load, because look, your force is just at the middle. The 400 lb force is just at the middle of your beam. So by symmetry, if you want, by symmetry you can directly say that Ay is equal to FCY is equal to 400 over 2. In this way, you can directly say that AY will be 200 instead of doing the calculation, okay? And FCY is 200. FCY is equal to 200. So force FC is equal to 200 times 5 over 3, okay? So this is an easier way to determine your reactions. And once you find FC, you replace into sum of X, you get AX. If you didn't pay attention for the symmetry in Y, to have AY equal to FCY, then you should write sum of X equals 0, sum of Y equals 0, and you should add a third equation, sum of moments. You can choose any point you want. Okay, you can do sum of moment about A or sum of moment about C. And even if you want, instead of sum of Y, you can replace it by a moment equation. So you can do sum of X equals 0 and 2 moments equation, sum of moments about A equals 0, and sum of moments about C equals 0. Let us try to do, for example, sum of moments about C equals 0. Then the forces doing moment will be Fr and Ay. Ax will not do a moment because, as you see here, Ax is along, it's passing by C, so no moment about C. So when you do sum of moment about C, you can directly get Ay, okay? Because doing sum of moment about C, let us write it here. Sum of moments about point C equals to 0. You have Ay times, I will take the positive, I will specify my positive direction. I will consider the clockwise as positive. Okay, so I have that Ay times 8. Okay, and for the resultant force, it's turning in the counterclockwise direction, so it's minus 400 times 4 equals to 0. So here you go back to the same result, that Ay is equal to 200. Okay. Now, once we find our external reaction, we are done with our external reactions. The next step is to do what? Now we can do the cut, because now we know the reactions at A, Ay, and Ax. Okay, so I can do my cut. When you do your cut here, you have two possibilities to find your internal forces. Or you take part AB, you do your analysis on part AB, or you do your analysis on part BC, okay? Because this section is a part of these two. So, and both will give you the same result for the internal forces. Why? Because you will follow the convention, okay? So if I choose to select AB, if I choose to select AB, I do this figure here, as you can see. I put AY and AX, which were calculated. I put, now please, here pay attention for something. Here you can never reduce the distributed load before the cut, okay? Because look, if you say I will reduce my system to only one force acting at the middle, it is not a good way to find internal forces at all. Because if you do a cut here, for example, then you would say, I don't have anything, any load before the cut, which is not true, because you have a distributed load before the cut. So always remember, I reduce my distributed load after the cut, not before it, okay? So here, I do my cut, I say, what do I have on this part? I have a distributed load, a rectangular distributed load of length 4 feet. So this rectangular distributed load can be reduced to one resultant force acting at the middle of AB, okay? And this resultant force has a magnitude 4 times 50, which is equal to this area and equal to 200, okay? Now, I want to find what are my internal forces. In 2 dimensions, as we introduced before, the internal forces are as following. You have the shear force. The shear force always trying to do rotation in the clockwise about the end of the beam. So you can see here that I should choose it downward to cause rotation clockwise. For the normal reaction, it's always positive when it's trying to do tension. It's causing tension in my beam. And my final force is my final internal moment is the bending moment, which should compress the upper part. So here it should be in the counterclockwise direction. Okay. Now, how to calculate V, M, and B? It's very simple. It's I apply equilibrium on this part because since my part is in equilibrium, any small part of it should also be in equilibrium. So now all I have to do to find my internal forces and moments is to apply the equilibrium relation on this part. So what I will say, I will apply the three equations. First, sum of x equal to 0. If I look at my figure, I have the normal reaction and B, and I have minus 266.7, which is AX. So minus 266.7 equals to 0. From this relation, I get that NB is equal to 266.7. Now, along Y, what do I have? Sum of Y equals to 0. Along Y direction, I have AY, which is plus 200. Okay. I have the shear, which is downward, so minus VB. And I have the downward resultant force, so minus 200 equals to 0. And I deduce so that VB is 0. Okay. And this is expected, you know why? Because when we have a symmetrical load on a certain beam, okay, if I have symmetrical load, then the shear will be 0 at the middle. Okay, so VB is 0, so expected due to symmetry. Okay, and now my final step will be to find the bending moment MB. Okay, so to find the bending moment, I do sum of moments. But can you tell me what is the best point to choose moment about? What is the best point to do moment about?
We can do about A.
We can do about A, but why I don't advise you to do about A? Because if you do sum of moments about A, you should include the moment of the shear force, VB. And if you have a calculation error for VB, then you will have a wrong result. Okay? So it's not wrong to do sum of moments about A, but when you do sum of moments about A, you should take the moment of VB about it. To avoid this, to cancel the moment of VB, I can take, in general, it's advised to take sum of moments about B, because if we have a calculation error for VB, it will not affect our result. Okay, if I do sum of moments about B, then the moment of VB and NB is 0. Here, the moment of AX is also 0 because it's passing by B. So I only have the moment of the reaction AY, of the force, and the bending moment. Okay, so let us write the relation for sum of moments about B. We have that sum of moments about B equals to 0. So we have, you should choose a positive direction. You can choose it as you want. If you want, since you choose MB, since the convention for MB is counterclockwise, I can put the counterclockwise direction as positive. And then I will put plus MB, okay? Now, if you look at your figure, the 200 Newton force is also doing a counterclockwise moment about MB. So it is plus 200 times the distance, which is 2. And you have for AY, which is upward, it's producing a clockwise moment, which is negative. So minus 200 times 4 equals to 0. So here you get that MB is equal to 400 plus 400. Okay, so MB is in the counterclockwise direction. If you get a negative value, this means that MB is in the clockwise direction. Any question until here? Okay. So now, if you want, let us try. If we choose the other part, we will obtain the same results. Okay? So if you do your analysis on this part, you should only pay attention to follow the convention. So since I considered this part now, I will have the shear upward, because we said that the shear is chosen in a way to rotate clockwise about the end of the beam. Okay? We should choose NB now directed to the left in order to cause tension. And we should choose the couple in the clockwise direction to compress the upper part of the beam. And as you can see here, by principle of action reaction, we have opposite forces. So if VB is downward here, it should be upward. So the convention is due to the principle of action reaction. And we choose this convention to have the same values if we select this part or this part. Okay? So now if I select this part, for example, and I want to calculate VB, I do the same procedure. So it is, I have sum of y equals 0. And I have that here I have plus VB. So VB plus, you have the component of FC along y. So plus FCY plus FCY, okay, and minus 200 equals to 0. So if you try it, you will get the same VB as before. Okay, and also for n, if you do n here to calculate n, you do sum of x, sum of fx equals to 0. What do we have? We have minus nb and plus fcx, which is fc times 4/5 equals to 0. So you get that NB is equal to 266.7 as we did in the previous slide. Okay, so any question for this problem? Can you? Yes, how we get the direction of VB? Yes, concerning VB, okay, VB is always selected in a way to rotate in clockwise direction about the end of the part. So if you select this part to do the analysis for this part, what is the extremity of your beam? This is the extremity of your beam, point A, okay? Your shear should be chosen in a way to rotate in the clockwise direction about the end of your beam. So to have VB rotating about A in clockwise direction, how should be VB? It should be down, okay? If you do the right hand rule here, you will see that VB is rotating in the clockwise direction about A. While if you take the other part, this one, what is your the extremity of your beam now? It's point C, okay? So VB should be chosen now to rotate clockwise about C. And to rotate clockwise about C, VB should be upward, like this. Okay, Christina? Any other question? Okay, another example. Determine the X, Y, Z components of internal loading at a section passing through point C in the pipe system. Neglect the weight of the pipe and take F1 and F2 equal to, for F1 minus 80I plus 200J minus 300K, and for F2 you have 250I minus 150J and minus 200K. So now, what we want to do is to find the internal forces and moments at point C. Okay, so here, as I will do section at C. But look, before doing section at C here, do you need to find the external reaction? Who can tell me there is a need to find the external reactions here, yes or no? And if not, why? What can I do? Look, when you do a cut at C, you have two possibilities. You can do the analysis of this part, or you can do the analysis of the other part, this one. Okay, of course with F1, so this part. Who will tell me which part is easier to do the analysis on and why? Look, if you look at this part, do you have external reactions on this part? No external reactions. The external reaction is the fixity here, and the fixity is applied only is in this part. I don't have any external reaction on this one. This is why it is easier to work now with this part, because if I work with this part, no need to find the external reaction here. Okay, so I can reduce my I will reduce the time for calculation, because if I want to take this part, I should first find what is the external reactions at my fixity, and because it's a fixity, then what will be in 3D, a fixity will do which type of reactions? It will do a force in X, a force in Y, a force in Z, a couple moments in X, a couple moments in Y, a couple moments in Z. Okay, so if I want to take the first part, I should calculate first what is AX, what is AX, what is AZ, what is AY, and also the moment. So I should calculate MA, MAX, MAZ, and MAY. Okay, so to avoid this, a good idea will be to take the other part. Okay, so always choose the part that is easier, for which you need to do less calculations. So this is why we will take this part now. So no need to find the reaction at A. I will do just the cut at C, and I will keep this part only, the second part. Okay. Now, if I keep the second part, what do I have in the second part? I have the force F1. I have the force F2. And I should calculate at C my internal forces and moments. Okay. So at point C, since it's a 3D application, then I can say that at point C, I have a resultant force that can have three components, X, Y, and Z. And I have a couple moments that can have three components, also X, Y, and Z. Okay. Now, to find the components of my couple and force, the whole thing that I should do is to do equilibrium relation on the part I am studying. Okay. So if I take this part and I want to find MC and FC, I will apply equilibrium relation on this part. Now, let us write together the equilibrium relations. So for this part, I have two equations I can write. First, sum of forces, of course, as vectors equals to 0. What are my vector forces here? I have vector, so I have F1 vector plus F2 vector plus FC, which is the internal force at C, should be equal to 0. And since they gave me F1 vector and F2 vector, I can simply say that vector FC vector is simply equal to minus F1 vector minus F2 vector. Okay, and now I replace the forces by their expression. For F1, I have minus F1, which is plus ATI plus 200 minus 200, because I'm doing minus F1. So minus 200J. Look, it is given here. and plus 300k. And now minus F2, so minus 250 I plus 150J and plus 200K. Okay, so now this is equal to, you have along I 80 minus 250, so it is minus 170 I, and along J I have minus 50J, and along K it is plus 500K. Okay, so this is the internal force at C, and as you can see, it has three components, one along X, one along Y, one along Z. Now, to find my moment MC, I also now should write the second condition of equilibrium, which is sum of moments equal to 0. So now I will write that sum of moments about point C equals to 0. So I have, first, when I do sum of moments about C equal to 0, I cancel out the moment of what? The moment of FC. So this is why it's a good idea to take moments about C. And now, when I do sum of moment about C, first I should take the couple vector. So it's MC vector. Okay. Plus what? Plus moment of F1 about C. So I should take moment of forces about C. So first it's MF1 about C plus moment of F2 about C. Okay, equals to 0. Now I will replace, if you want, I will just put points to, I will name this point here